in our last video, we were able to come up with our objective function c equals 12x plus 19,000 over x, and we said we wanted to minimize that function. And we also found the domain of that function. We said that x must be positive, which means our domain must be 0 to positive infinity. We have an open interval here. So regardless of whether we have an open interval or a closed interval, your first step is always going to be take the derivative so that we can find our critical numbers. Now, I don't think this is particularly nice to work with right now because we would have to use the quotient rule there, and you can if you want to. There's nothing to stop you from doing that. But I'm going to rewrite that with a negative exponent just so that I can use my power rule instead. So I'm going to rewrite this function as c is equal to 12x plus 19,200 x to the minus 1 power. So I've just rewritten this so that it's a little bit easier for me to take the derivative of. So now when I take my derivative, let's say c prime, that's going to be 12 minus 19,200 x to the minus 2 power. Now I know I'm going to be working with this. I'm going to be doing a little bit of algebra to find my critical numbers. So I'm also going to rewrite this with a positive exponent here. That would look like 12 minus 19,200 divided by x squared. So there is my first derivative, which is great. That's what I need. I now need to find my critical numbers, which means I need to think about places where c prime is equal to 0 and places where c prime does not exist. Places where c prime equals 0. Let's take our derivative and set it equal to 0. So we'll have 12 minus 19,200 over x squared is equal to 0. And we want to solve this equation for x. So I'm going to add that negative term over to the other side. That'll give me 12 equals 19,200 divided by x squared. And then I'll multiply both sides by x squared so that I can get that x squared out of the denominator. So that'll give me 12x squared is equal to 19,200. I can divide both sides by 12. We end up with x squared is equal to, let me grab my calculator here, 19,200 divided by 12. I have 1,600. And then I would take the square root of each side. I'd actually end up with two critical numbers here. I would end up with positive 40 and negative 40. And actually, let me just double check. I don't want to make a silly mistake here. Yes, I have a positive 40 and negative 40. Now remember that we want to check and make sure that these critical numbers are in the domain that we stated. So I'm going to go back and check. Remember, our domain, we said x has to be positive. Our domain was 0 to positive infinity. Well, 40 is in between 0 and positive infinity. That's a positive number, so that's fine. But negative 40 is not between 0 and positive infinity. We can't have a negative x value. So that means we're not going to think about x equals negative 40. We can ignore that critical number, which is good. It's a little bit less work for us. So that was the first case. I also need to think about places where c prime does not exist. So I'm going to look at my derivative. I'm really worried about where that denominator is equal to 0. So I'll say, okay, if I take x squared and set that equal to 0, and I solve, I can just take the square root of each side real quick. We end up with x equals 0, which looks like another critical number, but remember, we want to check to make sure that that critical number is in our domain. Well, 0 is not included in the open interval 0 to positive infinity. We used an open parenthesis right here to show, hey, 0 is not included in this interval. So because we have this open interval, that means that x equals 0 is not in our interval. It's not in our domain, which means that it is also not a critical number here. So that's, again, good news for us. It's just a little bit less work here. So that means we have our one single critical number of x equals 40. How I proceed with this then depends on whether we have an open interval or a closed interval. So I'm going to look at my domain. We said our domain was 0 to positive infinity, and in this case, we have an open interval. So on an open interval, that means that we need to hopefully have exactly one critical number, which we do. We only have x equals 40. At this point, now we just need to show that x equals 40 is in fact a minimum. So you can do that using either the first derivative test or the second derivative test. Either one will work here. I'm going to use the second derivative test just because I like it a little bit better. I'm going to copy this first derivative down here. So here is c prime. If I take the derivative once more, c double prime, derivative of 12, that's going to be 0. Let's see, 19,200 times 2. I should have a positive 38,400 x, and then I subtract 1 from my power, should now be to the minus 3 power, or 38,400 divided by x to the third. So for my second derivative test, I want to take the one single critical number that I found, which was x equals 40, and I'm going to plug that into my second derivative, because I'm trying to show that this will hopefully give me a minimum. So c double prime of 40 is equal to 38,400 divided by 40 raised to the third power. Oh, let's see. And in this case, I ended up with a positive 0.6. Now remember, for the second derivative test, it's really the sign that we care about. In this case, the second derivative is positive. Well, the second derivative tells me concavity, so that means since the second derivative is positive, our function is concave up, which means that we do, in fact, have an absolute minimum. So yes, we do in fact have the minimum. That's exactly what we wanted. So that's great. X equals 40 is in fact a minimum. That's wonderful news for us. Last thing that we need to do to finish this problem up then is to make sure that we're actually answering the question here. So I might go back and scroll all the way back up to the beginning problem and think about what it was that we were asked to find. So let's erase some of this. We can focus a little bit better. We wanted to find the dimensions of the rectangle that will allow for the most economical fence to be built. We wanted to find the dimensions of the rectangles, meaning we wanted to find the side lengths. Now we said x is equal to 40, so that's great news. We've already got one of them. We said x is equal to 40. We need to know what is y. And I would look through your work that you've done. In particular, I would look at the constraint that you have. In this case, we've got y equals 800 divided by x. And what I can do is I can just take x equals 40 and plug that into my constraint equation. We said that y is equal to, and again, I'm just looking at this piece right here, 800 divided by x. So y is equal to 800 divided by x, but we said x was 40 feet. That was part of our answer. Oops. So I'm just going to take 40 and plug that in for x. So y is equal to 800 divided by 40, which means that y should be 20 feet. So that is our missing dimension. We have one side, the side with the two cheaper materials, that's going to be 40 feet, but the side that has the more expensive materials, that side is only going to be 20 feet for our answer.